Hello everyone, I welcome you all to the course UAV design, and in today's lecture we're going to see the conceptual design of an unmanned air vehicle. Introduction to UAV conceptual design. Conceptual design is the first and most important phase of a UAV system design and development. It establishes the function, form, cost and development schedule of the unmanned air vehicle system. It also gives the need analysis, which defines the design requirements and serves as the foundation for system specifications. Systems engineering plays a critical role in defining and addressing system requirements from an integrated life cycle perspective. The objectives of a conceptual design are to develop and define specific design to requirements for the system, to identify the problem and define the need at the conceptual level, select an optimal system configuration which meets customer requirements. These are generally given by request for proposal or request for information. It comes between, if it is from the client for a specific project here refers to mission, and if an existing aircrafts are available, and then what are the missions it gonna take, that is RFI, request for information. It conducts initial planning and evaluation of relevant technologies, the cutting edge technologies which are used in this. The major activities in UAV conceptual design includes selection of UAV components and their subsystems. The major components: defining the UAV configuration and its three-view representation, which includes front view, top view, which is also called plan view, and side view. Evaluating the design alternatives based on past experience and trade-off analysis. Here, past experiences, the historical trends. This is historical data which is available. Based upon the historical data, it can be in the form of feedback, airworthiness reports, or the data which has been preserved by the designers and the flyers who use them in day-to-day life, and what they experience at particular mission, at particular altitude, how it is varying. Suppose during this phase, from ground roll to the takeoff, then climb, cruise, then descent, then land, during this phase, how the unmanned air vehicle has behaved. So that data will be stored, and based upon those experience, we can change our design. This is the design process and formal design reviews. Here, once we have the RFP, that is request for proposal. So from request for proposal, we'll get the requirements for the unmanned air vehicle. So once we have the requirements, from there we'll move to the conceptual design. From conceptual design, once the conceptual design is done, it goes to the CDR. It's committee for which verifies this conceptual design, and they'll go through the requirements, and then they'll go through the conceptual design which is being developed. Once they approve, it is been sent to the preliminary design team. If there are any changes with that feedback, it has been disapproved and it sends back to conceptual design. If it is disapproved, okay, it is disapproved. If there are any changes to be done, it goes back to conceptual design. Else, it will come to preliminary design. Same after this preliminary design, once the design is done, it goes to PDR committee. If it approves, it goes to the design part 1, or else it goes with the feedback to the preliminary design. Based upon the team here in preliminary design, they'll decide whether to modify here at this stage, or they'll send it back to conceptual design team. Again, after this PDR is done, it goes to detailed design part 1, and then it goes to ETR. If ETR approves, it goes to the further detailed design part 2, else with the feedback it sends to detailed design part 1. So again, the team here, again they will be work on it, and if it is at this stage, they will modify it and they will send it back to ETR for further verification and to get their approval. Else, if it is not sorted here, then they will send it back to preliminary design phase. This is a step-by-step process, and once it is approved here, then it goes to the design part 2, and then FDR committee will be approving it for production and construction. And if FDR team sorts that there is a change required in the design, it will disapprove and it will send it back to design part 1, not to design part 2. It will go to directly design part 1. And after all these steps is being followed, then the final it goes for fabrication, which is production, construction or manufacturing. So basically, UAV design requirements are: what is a mission? What kind of mission your unmanned air vehicle is supposed to take? What performance measures you want? What kind of performance you are expecting from the unmanned air vehicle? Stability, control, cost, operational, time. What is the manufacturing period? What kind of payloads it going to accommodate in the fuselage? So once we have these requirements from the RFP, in the form of RFP, request for proposal, once we get these design requirements, then we'll identify the major components required to satisfy these requirements. Right? And these major components of the unmanned air vehicle are how the wing should be, how the wing should look like, how much lift that wing gonna generate. Next, second one is tail configuration. What kind of tail configuration the unmanned air vehicle gonna have? Whether it will have a conventional tail, T tail, V tail, H tail, right? Because from the tail, it has to provide even horizontal stability, which is longitudinal stability. If you see, this is an unmanned air vehicle, right? If this is the vehicle, so it has to give stability even in this longitudinal axis. And if we see in the top view, right, this is the tail part, right? So even here, this directional, in what direction it will be? It will be moving in this direction. It will be moving in this direction. This directional stability is achieved using tail configuration. Then the third major component what we have is fuselage configuration, because it decides the amount of payload which it can accommodate. There are various payloads which unmanned air vehicle is supposed to carry. For example, the equipments and devices, autopilot system, and even a small cabin pressurization system to ensure that equipments are not overheated. The next major component in the conceptual designing phase is the landing gear configuration. What kind of landing gear your unmanned air vehicle going to have? Whether it's going to have the conventional landing gear, or it will have a bicycle type of landing gear, bogie type landing gear, or it's a tricycle type of landing gear. It again depends, design to design. Next, engine configuration. Engine configuration in unmanned air vehicle system, it generally is to just show the reflection how and where it has been mounted. Suppose if it is mounted under the wings, if we see this as a front view, if it is mounted under, if it is podded under this is the location. Generally in the conceptual design phase, the engine configuration will just give us the location where it is been placed. And in most of the unmanned air vehicles, these engines are buried type. If you see here in this picture, this is a buried engine which is inside the fuselage, which is been covered with the skin. Next we have autopilot configuration. This autopilot configuration generally it gives us the navigation and control. It gives the navigation and control systems. Next we have payload configurations. Again, this payload configurations is divided into various categories like equipments, devices, then cabin pressurization system, autopilot system, and any other sensors or whichever is required for the mission specifically. That all will be planned together, and these all payload configurations will be installed in the fuselage. Depending upon the payload requirements, we'll design our fuselage. Right. Once we have all this wing, tail, fuselage, landing gear, engine configuration, then a conceptual sketch has been drawn, like how it looks in the side view, how it looks in the front view, how it looks on the top view. This is a conceptual sketch. This is not the final sketch. During the conceptual sketch, if the wing is below the fuselage reference line, if this is the fuselage reference line, okay. So below this fuselage reference line, after the end of the design, detailed design, or at the time of production, there might be a change in the wing. Instead of having it here, it may go to even a high wing position. Here it is at a low wing position, which is below the fuselage reference line. At the end, after all prototype testing and all, there is a chance, there is a probability where this wing can be relocated to the high wing. Then this will call as high wing configuration. Again, if you see here, this is there is a chance that it may go to dihedral. As of now, it is looking like in the front view, it is the wing configuration is looking like anhedral. It may go to dihedral. It may have the configuration like this. As of now, it is anhedral. So there's a chance it may go for this dihedral. Okay, and then this is a top view, which gives the actual plan view of the wing, how it looks like. Here it is like a taper wing, right? It is a tapered wing. Here at the root, the chord root is greater than the tip root. This is the CT, right? This is the CR, right? So there is a change here, right? So after the initial phase of conceptual design, based upon the test and prototype testing data, there is a chance that even this may go to a sweep. This wing can have sweep configuration. It may be a regular sweep, or many designers, they are enthusiastic to even go with forward sweep. And again, it's based on the requirements of the mission. These wing configurations are varied, and the position of the wing is varied. So once this conceptual designing phase is done, the drawings are done, then the configuration optimization is been done, and then the UAV configuration is designed further. The primary components are fuselage, which is for payload accommodations, wing, generation of lift, horizontal tail for longitudinal stability. Also, it is pitch stability. Then we have vertical tail, which is directional stability. It actually, the rudder moves the direction, whether it want to change its direction, it want to turn, right? So all these are controlled using your vertical tail. Directions are controlled basically using vertical tail, and pitch up and pitch down are being controlled using horizontal tail. Then we have engine, which gives you the thrust, which is required to move your unmanned air vehicle. And in case if it is an electric engine, then we call it as power, generation of power. Then we have landing gear, which facilitates the takeoff and landing. Then we have control surfaces, which actually controls and which controls the maneuvers, the climb, roll, directional stability, right? These all comes under this control surfaces. Then we have autopilot system, which is for control, guidance and navigation. Then we have ground station, which controls and guides the unmanned air vehicle from the ground. And the last is launch and recovery, the major component, which helps us for launching and recovering the UAV. The major components wing, it provides a lift and contributes to overall stability. It ensures that aircraft is generating sufficient lift so that whatever the weight of the aircraft is there, it is being maintained during steady level flight. Horizontal tail, it controls the pitch stability. It ensures that aircraft is moving in steady level flight rather than being disturbed. Right? If there is any disturbance, right, here you can see it is moving in straight axis, and if there is any disturbance due to the gust load, there is a chance that nose part will be climbing up and this tail part is coming down. So, using horizontal stability, this flight condition is trimmed to regain its original position, that is equilibrium position. Vertical tail, it provides the directional stability. It ensures that whether the aircraft has to move in the left direction or right direction, it is being controlled using vertical tail. We have a component in the tail which is this is rudder. This is rudder which is being used for this directional stability. This rudder is moved. It is fixed with a hinge support. It moves in left direction and right direction. Based upon the movement of this, we control the direction of the aircraft. Then we have the major component in unmanned air vehicle is fuselage, which accommodates the payload, avionics and propulsion system. So, if this is the aircraft, this is a nose part. Here we'll have the landing gear boxes where the landing gears are retracted and placed here, and then we have the boxes here where we have the our equipments, instruments, sensors, cabin pressurization system, and this is the engine which is buried inside the fuselage. It generates the thrust. In propulsion system, it generates the thrust for a UAV movement. Landing gear, it enables takeoff, landing and ground operations. Control surfaces used for maneuvering and stability control. Autopilot system, it is responsible for guidance, navigation and control. Various configurations and alternatives exist for every UAV components. Designers must select one alternative per component based on the trade-off analysis. Trade-off analysis compares the pros and cons of each alternative in conjunction with other components. Optimization is required for mission-specific requirements such as payload capacity, range, endurance, and performance parameters. The configuration selection and trade-off analysis includes, for example, we have a fuselage, right? And the configuration alternatives for this is, in case of it is geometry, we have lofting technique or cross sections we need to choose. Then we have internal arrangement, and for example, what has to be accommodated, like payload, fuel, engine, landing gear. What all the components or what all the payloads are to be accommodated in this fuselage, it has to be decided. Then when it comes to wing, we have various options. What type of wing we have? Are we going to use swept wing, tapered wing, dihedral wing, anhedral wing? Right? Depending upon the configuration of the wing, we can choose. Next, based on the position, whether it is a low wing, mid wing, high wing, or it's a parasol wing, we need to choose even the location. Again, wing will have high lifting devices. Does it has a flap? Does it has a slot? Or does it has a slat? Even it has to be decided. Then attachment. Generally, all wings are an example of cantilever beams, or it will be a strut braced. There will be a support. Suppose mostly the high wing configurations, we give a strut support. Right? If it is a cantilever beam, but it is given a support here. This is strut based. Then for horizontal tail, we have the various types. We have conventional horizontal tail, T-tail, horizontal tail, H-tail, V-tail, inverted V. We have to choose based upon our mission requirements. We need to choose what kind of tail we need. Then installation, whether it's a fixed, moving or adjustable. That if you know the difference between stick free and stick fixed, which we generally study in control and stability, from this we can decide what kind of wing configuration, tail configuration we need in the horizontal tail. Next we have vertical tail. It will have a single tail, twin vertical tail, 3 vertical tails and V tails. Depending upon our objective, we can choose the vertical tail. Then again in engines, we have multiple options. What kind of engines we gonna use in our unmanned air vehicle? The first one, turbofan, turbojet, turboprop, piston prop, rockets or electric propulsion. Then again, when it comes to location of this wing, we have various options. The first one under fuselage, the second one under wing, beside fuselage, or it is buried, it is inside the fuselage. And then again, number of engines. We may have 2 engines, 3 engines, 4 engines, depending upon the requirement, or we may have only 1 engine which is buried inside the fuselage. Then even for landing gears, we have various alternatives. We have fixed, retractable, partially retractable. Locations, we have multiple, near the nose, tail or multiple locations. Next, control surfaces, it is to separate versus all moving tail. It is reversible versus irreversible, conventional versus non-conventional. Example, here it is elevon. It's a mixture of aileron and elevator. And then we have rudder waiter. Already we have a control surfaces like aileron, rudder, then elevator. Right. So it may have the combinations of these elevon, that is combination of aileron and elevator. Then we have a combination of rudder and elevator, that is a rudder waiter. Depending upon the requirement, we can merge them. If we have tailless aircraft, then we can go for elevon, or if we want to use only one control surface, then we can go with rudder waiter, which can provide you both horizontal and directional stability. This is horizontal, here is termed to longitudinal stability. Then we have autopilot systems. There are various autopilot systems available. We can choose as per our designs. For example, linear model, non-linear model. Then we have controllers, PID, gain scheduling, QFT robust. Then we have guidance subsystems, navigation subsystems. The last major component is launch and recovery, which is HTOL, horizontal takeoff landing, ground launcher, net recovery, belly landing. These are the various launch and recovery systems which we use generally in unmanned air vehicle conceptual design. UAV design requirements and the components which influence. Here each design requirements affects multiple UAV components. Every aspect, every component which we are going to choose, it will have multiple effects. Example, if I am choosing payload requirements, if there is an increase in the payload requirements, it will affect the maximum takeoff weight. Then engine selection, then the fuselage design and flight cost. These all areas will be affected if I am increasing the payload requirements. In case if I decrease the payload requirements, the MTOW will go down. Automatically the engine selections, engine selection criteria will change. Then fuselage design parameters will change, and this will lead to change in flight cost. A second example in this case is performance requirements. For example, max speed, stall speed, climb rate. This will affect wing area, and engine power. Stall speed and climb rate will directly affect your wing area, and max speed will directly affect the engine power. Designers must analyze payload weight and volume constraints for optimization. For example, payload weight requirements. So this will affect maximum takeoff weight, and when it comes to payload in terms of volume, in the criteria of volume, it will affect the fuselage shape. Then performance requirements, range and endurance, it will affect MTOW, that is maximum takeoff weight. Performance requirements like maximum speed, rate of climb, takeoff run, stall speed, ceiling, and turn performance, this will affect engine, landing gear, and wing. Stability requirements will affect your horizontal tail and vertical tail design. Controllability requirements will affect your control surfaces, for example, elevator, aileron, rudder, or autopilot. Autonomy requirements will affect CG, autopilot, ground stations. Airworthiness requirements will affect your minimum requirements and autopilot systems. Cost requirements affect materials, engine, weight, etc. Timing requirements will affect the configuration optimality, and trajectory requirements will affect the autopilot. So these are the various design requirements which has their effect upon the most of the components, most of the areas. Multidisciplinary design optimization. MDO is an engineering approach using optimization methods to solve complex design problems. It integrates multiple disciplines like aerodynamics, structures, propulsion, control and navigation simultaneously. Simultaneously, optimization yields superior designs compared to sequential discipline optimization. Researchers in academia, industry, and government actively advance MDO for UAV applications. In this lecture, we have seen the conceptual design lays the groundwork for UAV system development, and a proper selection of configuration and components ensure performance and mission success. Trade-off analysis and MDO techniques play a crucial role in achieving optimal design solutions. These are the references used for making this lecture. The first one is Design of Unmanned Aerial Systems by Sadare, John Wheely & Sons Limited. And then Aircraft Design, a Conceptual Approach by AIAA, and Introduction to Flight by Anderson. These gives the base of understanding the primary operations of primary control surfaces and secondary control surfaces which we use. And when it comes to the conceptual design approach, this book, Aircraft Design, a Conceptual Approach, gives a clear understanding how an unmanned air vehicle should be conceptually developed. We end this lecture here. We'll meet in the next lecture. Thank you.